This is a talk on grpc with C++, and some generic solution. So welcome, everyone. My name is Irakleia Karyoti. I work as a senior software engineer in Altair Engineering. For those of you who don't know Altair, Altair is a global leader in computational science. It provides software solutions for simulation, HPC, data analytics, AI, and much more. If anyone wants to know more, you can visit the website, and you can even ask me after the talk, or you can contact me by email. So today we're going to see a solution in order to embed gRPC into existing applications that probably have some older complex designs where it's not very easy to discretize or componentize some functionality we need to share among apps by using the client and server applications existing data model. So what we're going to go through, we are going to go through some theory first, basics. What is gRPC, why use it, the protobuf serialization mechanism that is commonly used with gRPC, some info on how to build, install, and use gRPC. Next, we're going to go through the basic features of gRPC, naming RPC types and the service API types it provides. We are going to see the standard approach, like the common approach, when you are going to create new services to use with gRPC. We're going to see an example, simple example, the restaurant example. The auto-generated APIs that are provided by gRPC, see why we do not want to use the auto-generated APIs. And next, we're going to move to another approach by wrapping up gRPC and protobuf to a new library and make it possible to use generic services that have no direct gRPC dependencies. See the benefit we get, of course, that goes along with some cost. So what is gRPC? gRPC is a remote procedure call framework. G stands for Google. This was originally created by Google. It is very modern, open source, high performance. It connects services in and across data centers, connects devices and mobile applications and browsers to backend services. It gives you all the support you need for load balancing, tracing, health checking, and authentication. It comes in multiple languages, and it's cross-platform. On the bottom, you can see the websites where you can get all info for gRPC and the languages it supports. Now, protobuf, again, provided by Google, is the common serialization mechanism that is used along with gRPC as a serializer for structured data. It is language neutral and platform neutral. It generates native language bindings. It is smaller, much faster than other formats like JSON or XML. And talking about protobuf, we not only mean the definition language in our .proto files, but also the code that the proto compiler generates and the serialization format for the data. So to use gRPC into your apps and services, first you need to clone a repository from GitHub, naming the release tag that you like. There are very clear instructions on how to build with Bazel, and this is what gRPC recommends. You can also use CMake. You will have no issue with CMake also. And you will need to get the proto compiler and all other dependencies. Again, the instructions online are very clear and very straightforward. So what are the common RPC types that gRPC provides? First, we have unary calls, where the client sends a signal request to the server and gets one single response back. We have server streaming. Again, the client sends a single response. It gets a stream of a sequence of messages to read back. There is client streaming, where the client writes the sequence of messages to the server and gets one single response back. And then there is bidirectional streaming, which is the most generic of all, where both the client and the server exchange a sequence of messages to read and write back. Now, on the service API types, currently gRPC provides 3 basic service API types. It is the synchronous API, named also blocking. The client sends a request to the server and blocks until completion. The server immediately responds back with the outcome and the status of the call. There is the async API that binds a completion queue to an RPC call, and the server gets to handle multiple requests at the same time. There is also the callback API, which is again an asynchronous API. The difference here is that gRPC directly calls user-specified code at the completion of the RPCs, and that is done through the usage of reactors. There are also some mixed mode service API types that combine messages types with the API types. We have the raw API in an asynchronous mode. This is a complete async API that uses a raw byte buffer as the request and the response message type. There is the raw callback API, which again is a callback API, and the message types are using a raw byte buffer. And then there are the generic APIs that come as async and callback. Again, the message types are just raw byte buffers, and they accept all RPCs and hosts, and the difference is that they can initiate an RPC by name, which is mainly what we want. So we had to choose among the two for our solution. The generic callback API is the one that we are going to use, and you will see as we move forward how and why. Differences between async and callback API. On the async API, we're using a completion queue for our RPCs. It is the application that must provide and manage its own threads. So the application must poll continuously the completion queue to determine which async actions have completed. And it is the application also that is responsible for executing any action upon an RPC is complete, notified by the completion queue. On the callback API, the user code is run from the library's own threads. This is a reactor-based API. There is no explicit polling required for notification of completion of the RPCs. And the library is responsible, as we said before, for executing any user-specified code at the completion of the RPCs. So this is what we chose to move forward with. Now, let's see a simple example of using gRPC the standard way, as I call it, using a simple client and server architecture. So on the right, we have the server. The server, in this case, provides, for example, one service, and in the process, I call it an order service, with some methods grouped under the service. And again, it publishes the message types that is going to exchange with the client. That is done through a .proto file that we will see on the next slide. So on the left, we also have one client. And when the client comes in, he would like to make a request to the server. Now this is where grpc fits in. So grpc will be available for the client to make an order. In this case, the client will say, hi, I would like some lasagna, a salad, and a glass of wine, and then the client will initiate a call to the server through grpc, and the client will decide that he is going to block until the completion of the call. So this is a synchronously called RPC. Another client comes in. The client again will make an order, say I would like a cheeseburger and a Diet Coke, please, and will start another RPC to the server through grpc. And client 2 decides that she will make a phone call until her meal is back. So this is an asynchronous process. So how do we model that using grpc and protobuf? This is the .proto file where the server initially will publish the services it provides along with the message types. You can see here we have one service, order service. This is grouping a few methods. Here we only have one for simplicity. It's called prepare meal. It takes one single request named order, and order is defined as a message containing 4 string fields: an appetizer, a main course, a dessert, and a drink. The server will process the request and gives back a meal to the client. The meal consists of food, which again we defined as a repeated field. That means a list of recipe fields. The recipe field can contain other things like ingredients or anything. And also a double field, which is the cost. So we start by providing that .proto file to the protocompiler, and the protocompiler will give us back some auto-generated code that contains the data model and the client library. We call that a stub. The stub is a component through which the client will interact with the server. So all these service API types that you saw before are accessible to the client through the stub. So originally we get 2 files with auto-generated code. One is the data model. Here you can see that we have 4 classes for the 4 message types that we provided. We have a recipe, a food, order, a meal. All those implement some basic protobuf message type. And they contain, they are ready to use classes. They contain copy semantics, move semantics, everything you need for efficient memory allocation, queries, and you can use all directly. But now the problem for us is that we already have these classes in our data model. So we would like to use that instead. Together with the data model, there is another auto-generated file that contains, as we saw, all the available service API types. So the simplest one, the base of all, is grpc service. This one provides a blocking API. So we see that the way to call prepare meal through the stub would be by providing a context, an order request, a meal response that we will eventually get back, and a grpc status, which is the status of the call that is originally returned right after. We have an async API that is called request prepare meal in this case. That also takes a context, a request, a response writer to get the response back, a completion queue for the client, a completion queue for the server, and we also need some unique tag for each RPC. The callback API, you see that in this case we call prepare meal. There is a special type of a context in this case to exchange, and again we give the order, we will take back the meal. In this case, originally the method returns a server unary reactor because we defined this method as a unary method. And through that reactor, we are going to react some way on the server side. And there is also the raw async API. You see that this is identical to the previous async API that we saw. The only difference is that now the request and message types are of type grpc byte buffer. And the same goes for the callback raw API, where again, grpc byte buffer is what we need for request and message types. So what do we need on the server side to call these APIs? Our services need to implement one of these grpc provided service classes. On the top, you see the blocking base grpc service. Then we have async service, callback service, and two generic service-based classes for the async and the callback APIs. So to implement and call a unary synchronous method named prepare meal, we need two implementations on both sides, on the server side and on the client side. On the server side, as you can see, we have some order service implementation that implements that synchronous base order service base class. And we define our prepare meal there along with its implementation, where we will create food, calculate cost, create a meal using that, and just giving those back to the client. And on the client side, our implementation needs to have a unique stub. In order to generate the stub, we need a channel of connection. So first we create the channel outside the class, then the stub, and through the stub we call prepare meal after we have calculated our input some way and transform it into a protobuf message type of type order. And then immediately we get both the reply and the status of the callback. So this is pretty simple and pretty straightforward. Now, on the other hand, if we need to call a bidirectional callback prepare meal method, we actually need two things. We first need to implement the reactors on both sides and the services, like we will see on the next slide. So the reactors, as you can see, we get one reactor on the server side named prepare meal reactor, and we have to do that for every method. That implements a server, a bidirectional reactor, taking an input of type order and giving an output of type meal. In this case, we get 3 callbacks, as you see, one for every read operation, one for every write operation, a final one named on done, which we have to implement as it is a pure virtual method. And we decide what to do upon every read and what to finally do at the end. Where does prepare meal method definition fits in here? Usually, as you will see on the examples on GitHub, you will see that they all use some next write method where they fit in the prepare meal calculation, and then they call next write upon every read after calculating the output. So on done on the server side will take us to on done on the client side. On the client side also we are implementing the same callbacks, every read from the server upon every write to the server, and when everything is done. The difference is that on creation of the reactor, on construction, we will use the stub to define that we are going to call prepare meal with the context next, and the whole thing initiates by using this start call. And the service in this case in both sides is implemented a different way. It will actually, in both cases, it will construct a reactor. So on the server side, the implementation is just giving back a new reactor, and everything is going to happen through that. And on the client side, again, upon construction of the reactor, the whole RPC is going to initiate. This is why we see a message on the bottom that your order is getting ready. So the RPC has initiated and it's being processed by the server. So everything seems good so far, but for us that didn't work quite well, because now on our applications we have added some direct grpc and also protobuf dependency with all the extra dependencies, compilation, and whatever else it needs. We also, on our server and client applications, those already share an existing data model. We would like to make use of our existing classes. If we choose to make conversion between those classes, that could be complex and inefficient, as these classes may contain a lot of information in some complex way. And also the third point, the existing APIs may not cover our needs. There are some things that you don't get for free with gRPC. For example, the raw or the generic APIs do not cover for unary methods. The raw APIs cannot be extended in the sense that mixing raw data with structured data is not possible, and at some point you may want to do that. And also, there is no clear objective on the callback APIs on where this service method implementation should be. Like you saw, we use next write in that case, but this is not clear. Anyone can decide to place that definition anywhere. So with that, we will move to a new approach, a more generic approach for the same example. So now that we're going to see a client-server architecture using a new library named mygrpc, what we're going to do, we will move this .proto file from the server to around grpc. We will add some generic services in there. Basically, only one is what you need. With a list of some generic methods and messages of more generic types that we will see. We will use this proto file to generate code that will be internal and hidden from the user, and we will use our own APIs to access the services that eventually the server will provide. So this is our new .proto file now. It is one and only, and it's hidden completely. The user doesn't have to know anything about protobuffer. You see that there is one service called mygrpc generic service. Here there is one method named call4, and you can name it whatever you like. Invoke sometimes is the most common. takes a stream of requests and returns a stream of responses. This stream now does not refer to a streaming process, but rather is used for message chunking. So in case of large messages, you can model that as a streaming process as the messages get chunked and read on a sequence basis. For the message types, we use a protobuf type of bytes for raw data. We can add some optional fields to denote the end of the message if we would like to chunk it anyway. So this is why it's optional. And this is like the most generic RPC signature of all. So given that proto file with grpc, we will wrap that and use some other components for our library. So what we're going to need is my grpc generic service that we saw before, some handlers for the methods, a service method call that uniquely defines one RPC, my service method reactor, which will be an implementation of a generic that we saw before, a generic bidirectional server reactor, and the same goes for the other side of the client. So again, we're going to have a reactor, a handler for the methods, a method call for each RPC initiated by the client, without, of course, my grpc generic service, which is only the implementation on the server side. And this is all internal. Nothing is exposed from these components. And the exposed components contain two types for request and response, which eventually wrap that protobuf message types. A server class in order to access the server APIs. My service, which will be now our new base for all of our services, and my stub, which will be the stub that we're going to use in the client to access the, to initiate RPCs and access the server services. So also we need to decide on what our common service method signature will be. Just like grpc, it has to be unique and common for all the methods. So looking on the data, my request and my response, the only thing that those provide is actually a standard stream for the client and the server to read and write back. And the library now is responsible to manage the lifetime of the request and the response stream. The client and the server only acquire this stream to make read and write operations. And behind the scenes, the internal implementation of my request and my response, as you see, also contains a my grpc request as defined in the generic.proto file, setters and getters, and possibility to slice the data. So getting the next slice once the message comes along. This is just the same thing that we talked about, only in code. So you can see that the internal implementation contains two things, a standard IO stream, but also a my grpc protobuf message type request. It has the possibility to get and set the next slice, and eventually get the grpc request in terms of, again, protobuf messages. The response implementation is just exactly the same as the request. So on the server, you will see on the right that we have my grpc generic service implementation, where this call for code, the implementation is, and this is the RPC entry point for each call we initiate from the client. So once an RPC comes there, it creates a generic reactor like we saw before. Through the reactor, everything happens. The reactor also performs any slicing that we would like to do for really large data. It creates a method called instance that includes an ID, name, maybe client initiator ID for each call. And we also have a handler to keep track of all the calls and manage the lifetime of the calls. And externally, we have my service. Now all of our services are going to implement just that. The my service implementation will contain a list of methods using the common signature, but also there is get method, and get method needs to implement it for each method in order to bind the particular method to a standard function object that we will be able to call by name. My server provides APIs like start, stop, register service. All those are quite the same, just like gRPC. So here is my gRPC generic service. You will see here that it only implements gRPC service blocking base class. But it doesn't matter because in here we can include any service API type that we would like, and we will see how as we move forward. So you can choose to implement call for the way you like, as a unary synchronous call, as a bidirectional streaming synchronous call, as a bidirectional callback call, like we do on the bottom. And this is basically what we do, what we choose, because this is the most general of all. So call for will take a context and return a type of server bidirectional reactor using protobuf my gRPC request and response. And returns my server method reactor, which is an implementation of such a reactor. This is the, the server method reactor that we have in our library. As you see, this is an implementation of server bidirectional reactor, so it includes all the callbacks that provides, including any other that we would like to add. There is on done, what happens on every read, what happens on every write, what will happen on cancel. And then that next write that we saw before, in this case, will call any of the methods that we would like that are provided by the server by name. This is the my service interface. As we saw, the only thing that we need to implement here is a way to bind our method with a standard function object that we are going to call. So if you see, this is an implementation of the previous interface, how we're going to implement now my order service in contrast with what we did before. So in this case, we have chosen to have a Boolean prepare meal method that takes my request as input and gives my response back as output. How to implement this? We get the service from the request. We will deserialize that using our own data model deserializer. We will calculate the response. So we will create the meal response. And we will serialize that using, again, our meal, in this case, serializer. And on get method, we will just, given the method name, there is a missing statement here, but if the method name is prepare meal, then we will bind that prepare meal to a standard function object to call. Now this is a basic difference on the server API. You will see that to start the server, in gRPC, we are doing actually one thing before really starting the server. We create all of our services and we register those services to the server. In this case, we have an extra step where we configure my gRPC generic service the way we would like. So how do we do that? We will use some gRPC internal APIs to create a service method the gRPC way. We will define the RPC type, as you see, as bidirectional streaming, the RPC type as callback, RPC, and we will add this service method to the service. So this is a way to define methods that you can use using any RPC type you want and any service API type you want. So you can have multiple methods with different service API types grouped on the same service. Then we registered my gRPC generic service. This is the common gRPC approach through a server builder of gRPC, and we start the server the gRPC way through the builder using build and start. And next, on the client side, what we're going to expose is a stub that will group all these method APIs for call for. Internally, that all will be handled through a method called handler. That again, it is a mirror approach of what we're doing on the server. So the handler keeps and manages the method calls, which remain live until completion. You can see that the RPC trigger point is basically through our generic reactor in this case, and that run method over there will start the call to access the server through the server reactor. So now you see what we can include on my stub now. I have added a call for blocking and a call for callback, but normally you wouldn't do that. Normally you probably would have just one API, or to make it more fancier and better, we would have like separate stubs, a blocking stub or an asynchronous stub. Like this is what happens in Java. The blocking API returns a status, and apart from request and response, it also takes a service name and method name to be able to call a method by name. The callback API for call for again takes a service name and method name, a request, and a callback. You can see with the signature of getting a gRPC response, giving back a response and a status, and this is a Boolean method. So there are 2 points here. In case we need to somehow simulate a streaming process, we may also use an API using a vector or some list of requests for the streaming calls. You can see that the context is missing here. This is because we define everything at a higher level and internally, but if you would like to exchange metadata per RPC, then okay, of course, we will add a context as an input. And now you can see that we can choose to return a status of our RPC. For example, if we need to make some monitoring on the client side for the calls, if we need that, we can also return a status. We can basically do whatever we like. Point two, yes, choose among blocking or callback APIs or combine the two, or just separate the stubs like we said. We have the option to add a callback even for synchronous RPCs, if this is something that we would like to add. Choosing the signature of the callback is one benefit we get. And also, if we already have some signaling mechanism in place, we can even completely omit the callbacks. We embed that, and our signaling mechanism will just signal through the reactors back to our code. So the change, if you see here, this is what we did before. So the standard way, we saw that we implement the reactors on both sides, implement the service on both sides. But now, if we would like to call prepare meal our new way, we will just have our callback, and from the client through my stub now, we will call for order service prepare meal, given a request, and binding that callback to the call. And on the server side, we will just implement get method to bind this prepare meal with some function object, and implementing prepare meal. So this is a very clear place where we define and implement all that. So what is the benefit that we got in the end? So we removed all direct gRPC dependencies on both sides. Now also the clients can decide on a synchronous or asynchronous or callback mode. Previously, this was just defined by the service. The service implementation was the one that decided how the clients will initiate RPCs. We get the ability to group multiple methods with different API types under the same generic service. We get more intuitive client APIs. We also get cleaner code. We now have the ability to add extra functionalities on a higher level, so for multiple services or even service methods, like we did with message chunking. The same we can do if, for example, we want to embed a progress callback or anything else on some higher level. And the cons, of course, since we are using our existing data model, all our classes need to provide their own serialization mechanism. So that alone increases again the development cost. And this is a C++ only solution. So there is no multi-language support for that. If we would like to use any other language, then the library needs to provide bindings for that language also. So as a summary, we saw a few things in theory about gRPC, how gRPC is used with protobuf and how it is used on newly created services and applications. We saw an alternative approach that we can use in our existing applications and our existing data models. And of course, since we actually paid the price of developing such a library, we got the extra bonus of the flexibility and the freedom that we could use in our newer APIs. So, thank you.
Hi, thanks for the talk. I have a question about changing the gRPC definitions over time with this break compatibility with like older clients that still use an older gRPC definition of my API, especially if I use the generated headers.
Changing the definitions of gRPC is even better handled in this way because there is a common new library that will be maintained by someone and not by everyone. So you will obviously have to maintain the library, and you have to keep up with any latest update, but that will also move to your client and your server implementations without any cost from their side.
Okay, so I can just update my gRPC and the client doesn't have to change in any way and can still use.
As long as you keep your APIs in a generic form that will not change over time, then you get the benefit of changing the implementation internally and with no cost on the server and the client side.
Thank you.
Hi.
Hi.
I sort of had the same question as before, but I want to be more explicit in when you want to change the schema of a particular message or payload, and how you handle API versioning specifically in parallel. So when you want to support multiple versions of your API, when you actually change fields in the schema.
The schema of that generic schema that you saw obviously will not change because it's only raw bytes. You will not change it ever. Now, of course, if you want to change the schema in your applications, the only thing that you need to maintain is your serializers. And that's it. That makes no actual cost for this library.
I would need to maintain 2 serializers, like for each version that I want to support in clients?
Yes, but in this case, okay, we are actually using a common data model in both. So you ultimately will have to do that, yes.
I would like to continue the tangent that we're already on. Is it now not the case that your client doesn't know your API anymore? If you use this generic situation, then you have just raw bytes. So if you want to expose some kind of API to your client stating these are the methods we support?
Yes, you will. Yes, actually, you will have to do that. For us, we're using some JSON, format to so that we reflect what kind of services and what kind of data we provide from the server to the client. If you want to do that without any connection, so just for discovery. Otherwise, if you would like to just reflect what is available on the server after connection to the client, you can have a reflection method included in your generic service that will basically mirror whatever is available from the server to the client. Reflection also is used by gRPC.
Okay, thank you.
Hiya. Still staying on a serializer, I think you might have answered some of my questions already, but what format did you use for your serializer? Did you stay with protobuf, or was it a custom serializer?
Yes, a custom serializer, just using a standard streams.
Standard stream.
Yes.
On the same page of the other questions is, one of the advantages of gRPC is that you can violate the API. You can violate the contract. So now you have this stream raw bytes. So did you have any issues with calling, for example, the wrong method with the wrong byte stream or something like that, and you maybe catch that bug in some ways in testing, for example? Any experience to mitigate these issues? Because this solution suffers the very same problems of JSON, that you basically can't statically avoid these kind of issues.
No, we have not. We didn't have such issues. But maybe you can avoid these issues if you use a variant instead of separate types. But so far we didn't have any issue.
Thanks a lot.
Thank you.